Hello and welcome to this Optica Technical Group webinar, Titanium Sapphire Integration for On-Chip Solid-State Laser Technology. My name is Makai Pruitt and I'm excited to welcome you to today's webinar, which is hosted by our Optical Material Studies Technical Group. The technical group has invited Kasper Van Gasse from Ghent University to speak with us, and we'll begin our presentation in just a moment. As you may know, Optica's technical groups have been hosting weekly webinars for many years now. Our group volunteer leaders organize and host these webinars to help bring you the latest in-depth information related to your specific research interest. In addition to these webinars, we host a wide range of virtual and in-person activities to help you connect with your fellow Optica members. We hope that you'll visit us at optica.org/technical groups to learn more about the 40+ groups, find out about our upcoming events, or access our library of over 200 on-demand webinars. Now, before we begin today's presentation, I wanted to review a few housekeeping notes. First, we will be addressing all of your questions for our presenter after their talk. We encourage you to submit your questions for our presenter throughout the webinar, and you can do so by clicking the Q&A button at the bottom of your Zoom window. You will then be able to submit your questions in the pop-up box, and you will also be able to see questions sent from your fellow attendees in that box, and you can vote for the questions you would like to see answered by clicking the thumbs up beneath each question. At the end of the webinar, we hope that you take a minute to provide us with your feedback by completing a short survey. Finally, this webinar is being recorded, and a link to the recording will be emailed to you following the conclusion of this webinar. Now, it is my pleasure to welcome Ivo, who serves as the chair of our Optical Material Studies Technical Group. He will tell you a bit more about the group and introduce you to our presenter. Ivo, the floor is all yours.
Thank you. Right, also welcome from me to this webinar on titanium sapphire integration for on-chip solid-state laser technology given by Professor Kasper Van Gasse from Ghent University. So I'm Ivo Tange. I'm the chair of the Optical Materials Technical Group. And before we get started, I wanted to present in a few minutes what we actually do in this technical group and what we can do also for you. So as you can imagine, optical material studies is a very broad umbrella term that encompasses a lot of different research. So just to summarize in a sentence, this is about materials with interesting optical properties ranging from the UV to the mid-infrared spectrum. So this can, like I said already, mean a lot of different things. It can mean that they have low loss. It can mean that they have interesting active properties like good optical gain, or maybe some nonlinear properties. The fact that this is such a broad term is also what I find interesting because we can explore some fun extreme possibilities in terms of both new materials, new applications, but also cutting edge research like what we will hear about today. So what do we actually do? Well, the goal is to create some sense of community between our different members. So we have a plus 2,100 members, and we want to do this by informing webinars like what we will have today, but also by doing networking, connecting events at typically Optica events to socialize and through reaching out on social media. You can see a few of our examples below here. So beyond me, there's a few other people in our executive committee to help organize these events. So we have Lam, Brian, Rana, and Sandra that help with this. So maybe you can recognize some pattern here. And the pattern is that we are trying to get some geographical diversity within our committee, meaning a person at least from each continent. So we have a little bit of the different perspectives from different continents. So as you can tell, maybe we're still missing someone from South America and Asia. So if you are interested in joining us and helping out, or if you know anyone that's interested, feel free to reach out to me and to us. How do you do this? Well, there's a few ways to keep in touch or to stay up to date. You can ask Optical to be on our email list by surfing to our website. You can join our LinkedIn or Facebook groups, or you can just email the email address that is given here. Having said all of this, let me introduce our speaker for today, Professor Kasper Van Gasse. So Kasper did his PhD at Ghent University in IMEC, where he graduated in 2019, after which he did first a postdoc at Max Planck Institute in Germany, and after that, another postdoc at Stanford University. And that's actually what he will talk about today. So at Stanford, the team where Kasper worked developed a titanium sapphire on-chip platform. First, a lot of work went into developing the platform, and then they also demonstrated amplification, so amplifiers on chip and also lasers. And with that, allow me to give the floor to you, Kasper.
Okay. First of all, thank you very much for the kind introduction, Ivo, and for inviting me to this webinar. It's of course always a lot of fun to give a talk here for the Optica community. And like Ivo explained, today I will talk about titanium sapphire work that I did at Stanford University. And let me just share my slides here for a second. Okay. Can everybody see this?
Yes.
Yes.
All right. Okay. So today I will talk about titanium sapphire-on-insulator for on-chip solid-state laser technology. This is something that I did as a postdoc in Stanford University in the group of Jelena Vukovic. And this was done with two co-first authors, Joshua Young and Daniel Lukin, who are now at a startup company called Bright Light Photonics, working further on this technology, and Daniel, who went to Harvard University. And then before I start with the technical content of this talk, actually the picture here tells already a lot. So for people who are not that familiar with solid-state laser technology, this pink cube that you see sitting on this quarter, that's actually a titanium sapphire laser crystal of 1 by 1 by 1 centimeter. And that's just a small part of what a tabletop titanium sapphire laser would be made out of. Now, this tiny needle that you see sitting against this titanium sapphire laser crystal, that's actually the titanium sapphire insulator chip that I will talk about. And this very tiny sliver of sapphire contains 25 tunable lasers. So I think this picture really summarizes really well the power of photonic integration, where we can go from, and this is just a laser crystal, big bulky setups, and just go to these very tiny, ultra compact laser chips. All right, so the rest of my talk is divided in separate technical sections. First, I will very shortly try to tell you a little bit more about the group I work at now, the Photonics Research Group of Ghent University and IMEC. And then for the titanium sapphire insulator, I will first talk about the platform and the context about that. And then later on into the talk, we'll spend some more time on specific devices and specific experiments. So I just very quickly wanted to include this. I'm currently professor at Photonics Research Group of Ghent University and IMEC. That's located in Belgium, and it's a very big group, and we all work on photonic integration, different aspects of that, going from telecommunication to life sciences. We're about 100 people, of which 12 professors, and so a very big group working on all aspects of photonic integration. But I am mainly working on laser integration for metrology and quantum optics. But you can see this picture with all 12 professors, and everybody works on a different aspect. And then finally, so we are part of Ghent University, which is one of the biggest universities in Belgium, with almost 50,000 students, and even presence in South Korea. Okay, and then finally, we are also an associated lab of IMEC. That's the Inter-University Microelectronics Center here in Belgium, who is really working on R&D on large scale, wafer scale, semiconductor fabrication, and also photonics. And our lab is in Ghent University, but we are associated lab of IMEC. That was a very short introduction to the group I'm at now. So now we can fully focus on the technical content of this talk. All right, so let me start with an introduction to laser integration, or the integration of lasers on photonic circuits. This is an effort that's been ongoing for a very long time. And that also shows, because if you think about laser integration in C-band, the most commonly used technology, frequency band for optical communication, you can find in literature very advanced integration strategies. So people are really capable of putting 3.5 gain into a multi-layer passive system. This is an example from UCSB, where they have 2 layers of nitride, a layer of silicon with photodetection modulation, and then they even can integrate the optical gain into that, and then make lasers and even microcombs, very advanced systems, all in a photonic integrated circuit. And even more recently now, EDFAs, so the fiber amplifiers that are used in long-range telecommunication, are now also, thanks to very low loss nitride, implemented in photonic integrated circuits. So you can see for the telecommunication band, laser integration is actually extremely mature, and the advancements are very inspiring. More recently, and that also has to do with ultra-fast optics on chip, people are starting to look also at different wavelength ranges for laser integration. For example, another rare earth type called thulium is becoming quite popular. And people are using that to make high-power Q-switched lasers on chip, and even femtosecond pulse amplifiers on chip. But this is all longer wavelengths. Thulium is about 1.8 micrometer wavelength. But now, in let's say the last 5 years, there has been an enormous uptake in the development of on-chip laser systems in the visible to near infrared. And that's really pushed by optical clocks, quantum systems, AR, VR, life sciences. So people are really looking to put new applications on photonic chips and getting new wavelengths on the chip that didn't used to be available. And here are a few, I think, quite important examples of that. So you have UCSB again, who demonstrated gallium arsenide lasers co-integrated with silicon nitride, really on wafer scale. Here's, for example, one of these wafers. Work from Columbia University, where people are combining visible lasers together on chip. And then a little bit more exotic examples, where, for example, also from UCSB, people are using very low loss nitrides to make BRIO-WAN lasers, but also at visible wavelengths, and that's for trapped ion control and cold ethics. So for sure, a lot going on, but one interesting trend emerged in the last few years, and that is actually that low loss nitride combined with rare earths and maybe aluminum oxide, so solid state gain, not semiconductor gain, is really opening new performance and new applications. So for example, here we have amplification of 100 femtosecond pulses. Something like this would be unthinkable with the semiconductor optical amplifier, or also called SaOI, due to nonlinearities, limited gain, etc. But this is now becoming reality. They almost achieved 1 kilowatt of peak power on chip. Moreover, now there are on-chip lasers that can give more than 1 watt and almost 2 watts of continuous wave output power. Again, with semiconductor optical amplifiers, this would be unthinkable. Also, erbium-doped silicon nitride, like the EDFAs, but then on chip, capable of doing high fidelity amplification of a Kerr cone. That's also not really possible within a semiconductor optical amplifier. And then finally, very narrow linewidth tunable lasers for coherent optical communication or quantum applications. So what's becoming clear is that the demonstrations in these last few years, where people put new solid state gain on photonic chips, really allows to make laser systems that are not realizable with semiconductor gain. So we're entering a bit of a new era of laser integration. One very interesting recent publication on the arXiv about this is also from the Kippenberg group in EPFL. So where they showed that they could actually do wafer scale implantation of this erbium in the silicon nitride waveguides, and showing that this is really a scalable process and that the solid state waveguide lasers are here to stay and to provide performance that was not achievable in the past. Okay. But then the question is, of course, that's all fantastic, but these rare earths, they usually are kind of limited to 1 micron to 2 micron, so infrared, not in the visible, not in the near infrared, where a lot of quantum applications and others are. Can we find another system that we could also put on a chip that can achieve the same performance, but at a different wavelength for different applications? And one such fantastic candidate would be titanium sapphire. So why titanium sapphire? It is really an amazing laser crystal. It has the widest gain bandwidth of any laser crystal available at this point. It covers about 650 till 1100 nanometers wavelength. That's pretty important for most quantum applications. And its enormous tunability makes it a single system that can be used for a really large number of applications. Also, thanks to this enormously wide gain bandwidth, you can have very good pulse amplification without gain dispersion. So this is really a very unique laser system. And except for the fact that it's very bulky and expensive, this is still one of the gold standards in laser technology. All right, so why, to give a little bit more of an insight into why it's so amazing, is on one hand, you have the host crystal, which is sapphire. For you who have ever worked with sapphire, sapphire is really the, how do you say, strongest laser crystal, you could say. It's extremely hard, very inert. It's a very mature technology. Sapphire can be grown in large quantities. It's also used to grow blue LEDs on top of this. So it's a very mature technology. And it has excellent thermal conductivity, which allows for the laser crystal to operate at high intensities without issues. The titanium inside the sapphire allows for a 4-level lasing system. Why is that important? Is that in a 4-level lasing system, there is no absorption, even when it's not pumped. So it's completely transparent at the lasing wavelength, even when the system is not pumped. And that allows, as we'll see in the future, a lot of interesting features. And then just to give some examples, so this is a very important laser system for quantum optics, to photon microscopy, OCT, all kinds of applications. And more importantly, or more interestingly, scientifically, Titanium sapphire was also used to build the first optical frequency comb ever demonstrated. This is a picture taken from the slides of Theodor Hensch, his Nobel Prize lecture named Passion for Precision. And so this is a picture of one of the first optical frequency combs. And this is titanium sapphire frequency comb. And actually, one of the challenges of working with titanium sapphire already becomes apparent from watching this picture. And that is namely that titanium sapphire lasers require enormous amount of pump power. That has to do with the fact that the fluorescence lifetime of the upper lasing level is very short. But concretely, what does that mean? Is that you will need very big and expensive pump lasers. And here you can see one in the top right corner. This is an 8-watt green laser needed to pump this optical frequency comb. And just the pump laser by itself costs about $50,000. It requires a chiller. It's very big. It needs to be bolted to an optical table. As you can imagine, it's just expensive and big. So it really stops people from using titanium sapphire lasers for real-world applications. They're not really ways forward to put this in a compact form factor and take it with you in a self-driving car or something like this. And so this has been something that many people have thought about and did research towards, is can we somehow reduce the need for the optical pump power to make a titanium sapphire laser work? And now what is the easiest way to do that is you don't want to change the crystal because that works really well. You more want to change the way you pump it. And when you pump something in free space, you're kind of limited by how far you can focus it down, while also having a long length over which the beam is focused. And that causes you the need for very high pump powers to reach a certain intensity. What's a very easy way to increase intensity while keeping the power the same, or even reducing the power, is using a waveguide, because it allows to make the mode area very tiny over very long length. And that allows you to have much higher intensity while keeping the power low. So people have been working on that for many aspects. So for example, pulsed laser deposited waveguides, even titanium sapphire fibers, titanium sapphire micro whispering gallery mode resonators. And then before our work, people even bonded titanium sapphire crystals on silicon nitride. And so what does this do? We try to constantly shrink the effective mode area, and that allows us to have much higher intensities for the same pump power, or dramatically reduce the pump power to achieve lasing, for example. All right, but so far, with all these approaches, a real high-performance titanium sapphire laser that can be pumped with a simple laser diode has not been demonstrated so far. So what we did at Stanford is take a step back and try to come up with a new nanophotonic platform that can really enable high-performance titanium sapphire lasers on a chip. And our approach builds on the expertise of the Vukovic group. I'll tell a little bit more about that in the next slide. But here you can already see a bit of the overview of the platform that we made. So it's a nanophotonic platform that's made by bonding, grinding, and polishing crystals, not by smart cut or not by deposition. And here you can see, for example, a microscope image of several titanium sapphire tunable lasers. We also made a little micro disk here with a Q factor of about 1.3 million that showed extremely low lasing threshold. We have made some nanophotonic waveguides, and then I'll go further in a bit of detail. So why bonding and tinning? This is something that was strongly developed in the Vukovic group. And the thing is that originally this was developed for quantum materials where you cannot accept the defects introduced by smart cut. So when you do smart cut, you implant at high energies, you create a lot of defects. But if you want to do color centers in nanophotonics or something similar, the defects you create too much noise, the quality is not high enough. So an alternative for that is really bonding wafers of material on top of a carrier wafer, and then first mechanically grinding or lapping it and thinning it down, and then finally polishing and or dry etching to get the nanophotonic thin film that you're looking for. And this also works great for titanium sapphire because it's a very hard crystal. It's not so easy to thin down. We figured out how to do it, but it's not trivial. And the nice thing about sapphire is that it also is very good for nanofabrication. People have been doing this for a long time, for example, to make micro lenses in the substrate of blue LEDs. And that is also something that is shown here. So we can take this thin film and then use pretty standard E-beam lithography and dry etching to make high quality nanophotonic circuits in this layer. Here you see, for example, an SEM image of one of these waveguides. We used a false color to indicate that titanium sapphire waveguide. But in the end, it's completely capped with oxide. And here you can see a very nice SEM image of the cross-section. So you can see this is the titanium sapphire and it's surrounded by oxide. And the nice thing here is that this is a very nice waveguide that will confine both the lasing mode and the pump mode very well. Now, of course, we did this approach to show, to enable very high quality crystalline material in a thin nanophotonic film. But of course, once we make the waveguides, we do have to verify that the bulk qualities of the sapphire are preserved. And this we did with the fluorescence lifetime measurement. And we clearly saw that indeed the fluorescence lifetime is about 3.1 microseconds, which is fully within what we expect for bulk at this level of doping and crystallinity. So this process really does preserve the, how do you say, pristine bulk qualities of the crystal, even when you go to nanophotonics. And then most importantly, by making the waveguide itself out of titanium sapphire and not making some hybrid waveguide, what we can achieve is that actually the lasing mode, so the fundamental lasing mode at 800 nanometer, will have a very strong overlap and be well confined with a mode for the green light. And that enables you to have very strong overlap, pump and laser, but also very high confinement. And that's only possible if you make the waveguide itself out of titanium sapphire and make it nanophotonic. And this allowed us to really go from all the steps that have been done before to somewhat of the theoretical limit of how efficient you can make your solid state laser by completely overlapping the mode and shrinking the modal area as much as possible. And this allowed us to push the threshold of our titanium sapphire lasers to below 1 milliwatt, what has never been done before. All right, but that's of course just the platform. That's the idea, and that works well. But of course, we also want to make usable devices out of this platform. And what is the first interesting device we can make with this is an actual titanium sapphire amplifier. In free space, this would not be so trivial to make, except maybe for high pulse energy amplifiers, because you would need to pump very, very hard to get significant inversion in the crystal to achieve high gain, right? But in our nanophotonic amplifier, due to the very tight mode confinement, we can actually get a substantial inversion. And this allows us to make actually an extremely broad bandwidth and high gain amplifier on a chip. And so here you see a small overview, and especially this picture is quite interesting. So this is a microscope image of the 8 millimeter long titanium sapphire spiral waveguide, of which the cross-section looks like this. and it's pumped with green light and then long pass filtered to make the microscope image. And here we see, it just lighting up in a very nice way. All right, so what is the first thing we did and we wanted to figure out is, okay, so we tinned this down, we made waveguides. Now we want like a hard quantitative number to understand how good this all works. And what we started with is just a very simple, straight, short waveguide that we can pump without too much pump attenuation. And then just basically send in a signal, a test signal, and then measure the amplification of this test signal as function of wavelength, and try to calculate back some material gain properties from that. So this is the result from that measurement. And what we can see is that we can get, this is expressed in dB per centimeter. So this is extrapolated from this measurement. So what we can see is that in principle, our waveguide would give up to 60 dB per centimeter of small signal gain. And why are we interested in this? Is because now we can compare one-to-one with, for example, the rare earth doped silicon nitride waveguide amplifiers. And then we see that we actually achieve almost 10x more amplification in our waveguides than in the rare earth doped ones. Moreover, we actually achieve gain over more than, I wrote it here in terahertz, but over more than 250 nanometer, or about 112 terahertz. And just to give you an idea, because sometimes it's a bit tricky to convert different wavelengths, bandwidths, having 100 nanometer at 1550, that would be already pretty wide gain bandwidth SaOI. That's only 1/10 of the gain bandwidth that we have here. And so this was just to extrapolate just the gain per unit length. But of course, we also want to make an actual amplifier that can amplify signals in a very compact form factor. Interesting to note is that this spiral waveguide is really only 0.5 millimeter by 0.5 millimeter, so extremely tiny. This is a fraction of any photonic integrated circuit. So you can put tens or even hundreds of these amplifiers on a single chip. However, it can provide extremely high gain over an extremely wide bandwidth. So instead of using this short straight waveguide, we now use the spiral. We pump that with a solid state laser, tabletop solid state laser to get a quite strong inversion. And then we amplify, I don't know, 100 microwatts output from our tabletop tunable titanium sapphire laser. And what we see is that we can get up to 20 dB of net gain. And again, that we have an extremely wide gain bandwidth. So that makes this technology very interesting, is that you can actually use this chip for almost any wavelength between 650 and 1100, all in this one technology. Moreover, the gain of titanium sapphire is extremely high. And for this 20 dB, we were actually mainly limited by the fact that the 7% reflection on the facets was already enough to make it lace if we increased the pump power. And so that was one of the limits on the gain we could get, which could be easily improved by a lot just using simple AR code. All right, then to explain a little bit how this compares to the state of the art, I like to use this graph from a paper from 2022 from Reza Morandi at Caltech, who made a very nice overview of gain per unit length versus 3 dB bandwidth for different amplification systems. And what you then can see is that, for example, this rare earth doped systems, they sit down here. They have pretty low gain per unit length, on the order of 1 to 3 dB per centimeter. And they also have pretty limited 3 dB bandwidth, depending on how you define this. You have some nonlinear systems that are basically optical parametric amplifiers that has a bit more bandwidth, a little bit more gain. SaOIs tend to have extremely high gain that's really unmatched per unit length. They can be less than a millimeter long and still amplify 20 dB. But then if you look at the titanium sapphire, you can see that the gain bandwidth of the TiSaph is really completely out there. It's much wider than any of these traditional systems, and even outperforms this very advanced optical parametric amplifier. And the gain is also quite high per unit length, still higher than erbium. However, still not on the level of an SaOI, which would be very hard to compare to. But you can see that we trust a lot that is a very promising system for future on-chip laser technologies. Okay, but then, so that was the gain bandwidth, gain per unit length. But we also want to understand, can we get actual power out of this system? The answer is yes. So we can get up to about 60 milliwatts of output power and still achieve about 7 dB of gain. However, in this case, we were mainly limited by the fact that this was one of the first devices we ever made. We still had quite some passive losses. And on top of that, cross-section of this waveguide is pretty tiny. And I think we can easily do a few hundred milliwatts with a slightly larger cross-section. But then finally, it's not only a great amplifier. What is very interesting about titanium sapphire is that the fluorescence lifetime is not ultra short, but also not extremely long. It's only a few microseconds. And that actually allows you to make a very nice incoherent light source, waveguide light source, with an extremely wide bandwidth. So this is about 100 terahertz. This is much wider than any SLED I know. It's also at a very good wavelength for OCT and other imaging, 800 nanometers. And because you can couple all the ASZ to a single mode waveguide, you can actually collect a lot of power efficiently that you then can efficiently couple to even a single mode fiber because it was all collected in this nanophotonic waveguide. So in short, this very promising amplifier technology for all kinds of applications. But very importantly, in recent years, the development of ultra-fast optics on chip has become quite important. So for example, this is the cover of Science from 2023, where people show that they made this tiny mode-lock laser at 1064 nanometer using thin film lithium niobate and an SaOI. And this was a very nice result, but because it was an SaOI, the pulses were still pretty low energy, long in time, and still not really there where we need it for really ultra-fast optics on chip. And that's really because of this gain material. The SaOI is still not what it needs to be. Similarly, from DAISY, we have some very impressive results where people made a Q-switched laser. This is really this tiny chip that can generate pulses up to 150 nanojoules. That really exceeds a lot of tabletop systems even. So really impressive technology. And then finally, and this is really the state of the art in ultra-fast optics on chip, people have also shown that you can make a femtosecond pulse amplifier in silicon nitride. And they can even amplify it up to about 800 watts of peak power. So very impressive, but still a long way to go compared to fiber amplifiers and other systems. All right, so what is now holding us back and what can we improve is that all the ultra-fast optics, or most of it, was done using rare earths in combination with silicon nitride. And that has some drawbacks. It has a lot of advantages. It's wafer scale. You can implant it. It has a lot of advantages, but it also has a few drawbacks. One of them is it's 3-level system, so it absorbs when it's not pumped. So that also means that you need very careful pump management in these integrated systems. But the gain per unit length is also pretty low. So you need a very long amplifier to get significant amplification. And that also means that you actually need to take a lot of dispersion engineering into account. And on top of that, silicon nitride has a very strong kernel linearity. And that means that you can have actually a lot of nonlinear deformation of your pulse. If you look at titanium sapphire, on the other hand, it's an ultra broadband gain profile. So it means that you have no gain dispersion. It's a 4-level system, so it doesn't really interact even when it's not pumped. So that really makes the pump management a lot easier. The gain is very high, so you can make your amplifier very, very short. And that means you will have to take less dispersion and other effects into account. And on top of that, the kernel linearity of the titanium sapphire amplifier is very tiny. It's only 1/10 of that of nitride. So you can get away with a lot more in terms of pulse amplification. So if you look into more detail at this tiny amplifier that we made, it's just an 8 millimeter titanium sapphire waveguide. And it can, because of the properties of titanium sapphire crystal, you can actually still get quite some gain, about 20 dB, for something that's less than 1 centimeter. So that's really amazing. That's very hard to do, combined with this very big gain bandwidth. On top of that, actually, the material dispersion is quite limited. It's pretty small. And that, combined with the fact that the amplifier is quite short, you can see that if you look at the pulse duration versus dispersion length, what you can see from this graph, if you ever worked with this, is that you can actually, for this amplifier length, you can amplify pulses as short as 100 femtoseconds and actually still get away with almost zero dispersion on the pulse. So that means that we can really amplify ultra short pulses with this amplifier without any degradation of the pulse. On top of that, because of the small kernel linearity and the fact it's also short, we have almost no nonlinear spectral broadening or phase accumulation of our pulse. And that's all the way for peak powers up to 1 kilowatt. So you have to imagine it's very tiny cross-section. You can go all the way to 1 kilowatt. That's starting to be on the order of 100 gigawatt per centimeter squared. So very high intensity. So that means that with this simple system, we can really do distortion-free pulse amplification on chip. And that was not really achieved before. And so to demonstrate this really unique performance, we just, with the simple device we made, this is the first amplifier we ever made, we amplified pulses from a multi-look laser we had. We did not have a femtosecond laser at the time, so we used a 2 picosecond multi-look laser. And then we amplified it in our amplifier. And using this system, we really managed to get a pulse energy of 2.3 nanojoules out of our chip. And that's really about 20 times the previous record. So this is really unmatched in terms of pulse energy. And we can also, I think this is still the standing record for pulse amplification on chip. We could get peak output powers of 1 kilowatt. And on top of that, from this experiment, we learned that the titanium sapphire waveguide, they really have excellent power handling. We could operate this for hours or days on end without any degradation of the performance. And this while we were at some point pumping about 0.5 watt of green light into this waveguide for hours on end without any degradation of the waveguide. So that's really very encouraging for high performance lasing on chip. Let me just, okay. So in short, we really think, this is just amplifier, that for the amplifiers, titanium sapphire is an extremely promising platform. We have a gain bandwidth, power handling, pulse amplification, CW amplification, that really seems to be beyond state of the art. So I think this will be very exciting in the future to see what will come. And then as the second part, we just also shortly want to illustrate that this amplifier can be incorporated into tunable lasers on the sapphire-on-insulator platform, where we can, this is again very compact, this is about 0.5 millimeter by 0.5 millimeter. We can make a very simple, widely tunable titanium sapphire laser with this very small footprint, tunable with just a simple microheater, achieving thresholds below 10 milliwatts. It can be single mode. We get pretty good stability. We can lock it using just this microheater. Instantaneous line widths on the order of 100 kilohertz. So a very high performance laser. I will, in view of time, skip the technical detail why this actually works so well. It has to do with the fact this is actually a non-resonant pumping scheme. So it's a very simple laser, but we just pump this waveguide as the gain section. There is no resonant pumping needed, and that makes it very easy to handle. It's very widely tunable. So this is, I forgot by heart, this is a few tens of terahertz. It's very hard to achieve actually with other gain media. And this is still only a fraction of what would be achievable. Even with a simple cavity and very short cavity length, we can already get line widths on the order of 100 kilohertz. And I think we can do much better than this. And then finally, and maybe most importantly, because we made our titanium sapphire laser so compact and so small, it is now possible to make a tunable titanium sapphire laser and pump it with this very simple TO-CAN diode laser. This costs about, let me see, $30. So making a fully integrated tunable titanium sapphire laser is really here after many decades of trying. Now you can really do it on chip and achieve the full tuning range. And this effectively makes the cost of this titanium sapphire, the pump section, go from more than 30,000 to basically $30. You don't need the chiller, you don't need the tabletop setup. And then finally, to just give an illustration, it's nice to say, oh, we're going to make titanium sapphire lasers on chip. It's good for quantum optics. But it's, of course, also interesting to really show that this is the case. So what we did is we made an array of these tunable titanium sapphire lasers on chip. And then we used them to control color centers in a silicon carbide optical resonator here. And what we did is perform this cavity QED experiment and actually compare the performance of a tabletop $500,000 titanium sapphire laser with our tiny on-chip tunable titanium sapphire lasers and really compare it 1-to-1. And that's what you see here in these graphs. So this is, for example, resonator scanning, an important operation during this cavity QED experiment, where the gray line is what happens when you do it with a tabletop sapphire laser. And then with our tiny lasers, we achieve the red line. And this is without any packaging or whatever. This is just because of the quality of the platform. We can already, with our $30 laser, get very close to the performance of this tabletop laser. And then, for example, in photoluminescence experiments, we again see the same thing. We have this very big, bulky, expensive tabletop titanium sapphire laser, which has a very similar performance to what we can achieve on chip. So very encouraging, but this is in many ways only the start, of course. Still so many challenges to be tackled. We have now made a tunable laser, but it only covers a very tiny part of the gain bandwidth. So what will be very interesting is how can we make widely tunable lasers that can really cover a wide range of this gain bandwidth. That's very challenging because you need to cover a very big range of wavelengths that will have different confinement, different couplers, and you need to somehow combine all of this. We've shown that we can amplify femtosecond pulses but we did not make femtosecond laser yet. So that's the next challenge, how to get satchel absorber on this chip, how to really make femtosecond laser. Then okay, we can make this thin film titanium sapphire, but as with most things, you often want to integrate it with foundry scale photonic platforms such as silicon nitride. So this is another challenge. How can we integrate this with silicon nitride? From preliminary simulations, it seems that it would be very reasonable to actually couple from silicon nitride to titanium sapphire-on-insulator. But that's something that needs to be explored and to be actually done in the future. And then finally, so we were kind of capped at 60 milliwatts because we were using very, very small cross-section to achieve low threshold lasing. But in principle, there should be the very high power platform. So we want to explore new geometries, rich waveguides, thicker waveguides. Sapphire has excellent power handling, great heat sinking, has some of the highest damage thresholds of any photonic material. So we should be able to push this a lot. And with this, I'm going to skip this. I would like to end my presentation and thank everybody for their attention. And thank again Jelena Vukovic for being so kind to host us to do this research. And of course, my collaborators, Joshua Yang and Daniel Lukin. Thank you very much. And I'm happy to take any questions.
Thank you very much, Kasper. Applause.
Thank you.
So we have a few questions in the chat already. I don't know if you can see them, but I can also read them if you want.
Where is this Q&A?
Yeah. So the first one is from Jamie Viegas.
Okay.
I hope I pronounced it correct. So maybe let me read it anyway for everyone. So the first question is, thank you, Kasper. Excellent talk and work. How stable is the bonding with the optical amplification thermal load cycles?
It's actually pretty good. So this is with the very high temperature bonding that we fabricate these chips. So the small amount of heat generated during amplification, etc., it has no influence on the bonding strength of the sapphire to the oxide. So it's that's for sure not one of the challenges that we're facing at this point.
Great. The next one is from Jue Wang, who asks, is it possible to use high purity silica glass wafers, I assume, to make titanium sapphire-on-insulator instance or sapphire crystal?
I think so, yeah, for sure. That would also work. I mean, we just chose a sapphire wafer without much reason. Let me just get back here for a second. So it's a bit of a, there were some reasons that we wanted to first try it with sapphire because then we could heat it up very well, etc. But no, you could do it on a quartz glass or an oxidized silicon wafer, or there's not really a strong limitation on the carrier substrate as long as it can support an optical mode with sapphire as the guiding material.
Okay. The next question is from Asima Mohanty, who says, thank you for the great talk. What are the challenges moving toward a femtosecond laser in the platform?
Oh yeah, what a great question. Thank you, Asima. So I think there are really a lot of challenges here. So far we kind of demonstrated separate devices. For the femtosecond laser, you would of course need to combine a lot of functionalities on a single chip, making it very challenging to how to say, actually realize this because one would need a satchel absorber, high quality mirrors, low loss waveguides, dispersion engineering, basically all the steps you need to do to make a fiber femtosecond laser or free space femtosecond laser. And you need to kind of do this all while also keeping the compact footprint, taking into account all the engineering challenges. So it is for sure doable. I think the satchel absorber is still the main challenge at this point. People have not really shown in literature how to put a satchel absorber, let's say, on chip. I think if that's solved, it's really within reach, but it will be a very big engineering challenge. Yeah.
The next question is from, I'm sorry, I'm going to probably mispronounce your name, Ji Eun Bai, who asks, what is the damage threshold for your current dimensions?
So it's a bit hard to exactly identify. It will be, of course, lower than for bulk sapphire because there are some interfaces and you have the silica around it. But it's still very, very high. So I don't think we ever figured out what we couldn't really blow it up because at 1 kilowatt peak power, like I said, you are really at intensities of a few hundred gigawatts per centimeter squared. So that's really extremely high intensities. I don't know by heart what the damage threshold for sapphire is. It will be very high. So far, we did not manage to destroy it yet. So that will be future work. Thank you.
Destroying it in the future.
Yes.
The next question is from Stevie Cordet, who asks, or who says, thank you for the presentation. What resolution do you achieve in your fabrication process?
Oh, yeah, thanks for the question, Stevie. So if you mean the resolution of the waveguide, it just depends on the lithography. We can do both deep UV and E-beam lithography. Let me see if we can find a slide here. So in principle, you could go as narrow as a few tens of nanometers. The only thing is for the dry etch that we used, there was a bit of a sidewall angle. So that kind of limits how small you can go. But yeah, I would say a few tens of nanometers if you use E-beam lithography. And then if you go to deep UV lithography, it will be, yeah, mainly limited by the resolution of your optical lithography system. Yeah, thank you.
Maybe since you're talking about the sidewall, let me piggyback on that question to ask one myself. So I'm just curious, indeed, with these sidewalls, have you measured the loss when you don't use a silica cladding? I'm curious how different it will be compared to the 1.3 million Q factor you got.
So no, that's a great question. So that's still a lot of ongoing work. So we get I forgot how much this was. It's like a few tens dB per meter. If you calculate it back from the Q factor. So the material itself is for sure not a problem. But you can even see it in this SEM. These are our first devices. I don't know if I have the slide here somewhere. So for sure, the sidewall roughness is one of the first challenges. Yeah, here. It's really on the order of a few dB per centimeter for the first devices. But it's, I mean, very similar to silicon or other platforms where you basically just need some optimization, yeah, to get this working.
Okay, we have another question from G, who asks, could you comment on possible strategies for longer wavelengths, like larger than 2 micron thulium on this platform, in this platform?
Yeah, so in principle, for guiding, sapphire is great. So sapphire is an excellent material in terms of material absorption. I think it's one of the purest materials you can get. It's probably much better than silicon. Well, not always, but could be better than silicon. So material absorption, etc. I think even in mid-infrared, this I'm not 100% sure, but is extremely small. So it could be a good passive platform for mid-infrared. But to get rare earths into crystalline sapphire, I think that's very challenging. one would need to do either post-laser deposition of sapphire, but then you would probably need to grow it on sapphire. So it's all possible. But titanium sapphire can just be different ways to fabricate that. So I think it would be very challenging actually to make a mid-infrared thulium doped crystalline sapphire laser, because it would be very hard to get the thulium inside the sapphire. Basically, would be my feeling. Yeah.
Okay, the next question is from Mikhailo Dubov, who asks, what are the coupling and propagation losses in sapphire-on-insulator?
Yeah, so like I said, so we for sure in this work there has been. You can also go to the Bright Light Photonics website, which is the spin-off company. There they can do, I don't know, less than a few dB per centimeter propagation losses. What I'm saying, less than a few dB per meter propagation losses, denk ik. So the sidewalls, you can mitigate them very well. I mean, I think they even do something like 10 dB per centimeter at 400 nanometer wavelength. If it's purely Ti-7 insulator, the propagation losses in the end will be just from the background absorption. Even though it's a 4-level laser system, there is some background absorption. And let me see if I have, do I have a picture here? Yeah, here. So, because this is a little bit how it works. So there's absorption in green, it decays through phonon emission. And then you have this emission. There is a little bit of a tail still at the lasing wavelength. And that, of course, depends on the doping. So the absolute limit on propagation losses in this platform, I think it's about 1 dB per meter to about a few dB per meter. If you can get the wave, the sidewall roughness really good. Yeah, I think that will be the ultimate limit for the Ti-7-on-insulator platform.
Okay, I apologize for the others, but we only have time for one final question. So
Okay.
let me choose the one from Bokun Zhao, who says, excellent talk. I am wondering how exactly the laser is coupled in and out. He assumes it's edge coupled. Is there any tapering of the waveguide, and how much facet loss do you have? And is there any treatment to improve the edge coupler loss? So basically, can you say something about the edge coupling?
Yeah. So it's really like in this 3D Blender figure, it's like this. So it's just it's not even polished. It's just a cut facet. So we just have a waveguide with the edge coupler, and then indeed it is kind of tapered down the waveguide to be very small, because we actually we do free space coupling to this chip. Because the pump and the laser signal are so different in wavelength, you cannot really use lens fibers for this. So we need to do a free space coupling to multiplex both beams. But that also means that you can actually focus the light on a very tiny spot. And so, yeah, the waveguide is just, the edge facet is just designed for high efficiency coupling. But I do have to say a very big challenge here is that when you do free space coupling, the quality of the free space beam starts to matter a lot to have high efficiency in coupling. That all being said, in the future, yeah, we probably want to switch to glued fibers, fiber arrays, something more mature fabrication. These were all really, how do you say, really research devices. So this is really only the start. Yeah, thanks so much for all the questions.
Well, actually, we have maybe, because there's just one more in the chat, so let's just answer it. It's also from Stevie Cordet, who asks, did you do a temperature control for the use of the chips during the tests?
So that's a great question. So I even have a slide on this. Yeah, for sure. So you do need to have some temperature control. There's also an analysis on this in the paper. You need to kind of be careful, because indeed, if this would get too hot, the quantum efficiency will start to drop. Now the sapphire is very good heat conductor, so it can handle a lot in terms of how much optical power you want to use, and but if you want to go for high power and really test limits, yes, you need temperature control. And if there's no temperature control available, it will still work, but you will need to do some engineering to ensure that nothing is how to say, suffering from increasing temperature. But from our simulations, you could go up to 300 milliwatts of lasing power and have actually very limited influence of the temperature. Yeah. But in our tests, temperature control, we sometimes used it, but I cannot say that it seemed to change a lot of things very often. Yeah.
Great. Okay, I think with that we can end the webinar here. So thank you again, Kasper, for your excellent talk. Very interesting work. And thank you all for your questions. I hope you enjoyed the talk. Yeah, thank you very much.
Yeah. Pleasure being here, and thank you for inviting me, Ivo. And I hope you all had a great time seeing this. All right.
All right, that will conclude our question and answer session for today. Please remember that when you disconnect, you'll be prompted to complete a quick survey. We will also be sending you a link to today's recording by email within 48 hours. I'd like to thank Kasper for taking the time to present for us today, and thank the Optical Material Studies Technical Group for organizing this webinar. On behalf of Optica, thank you for joining us, and this concludes today's webinar. You may now disconnect. Bye.